the way I like to do theorems is with if-then. So if something is true, then this is true because of it. Okay? So if you think of like Pythagorean theorem, if it's a right triangle, then a squared plus b squared equals c squared. Right? So it's an if-then. So any theorem that you see, I feel like it's much easier if you break it down as an if and a then. If something is true, then something else. Because sometimes theorems are just like, they're longly worded things that, I don't know, I just don't like them that way. But mean value theorem is still a pretty long theorem, but if you break down the ifs, it kind of makes it easier to understand, you know, what your output is. All right, so it says, if f of x is continuous on this interval from a to b, including the endpoints, and differentiable on that same interval, but you can't include the endpoints because the endpoints, the derivative has to match on both sides to be differentiable. Okay, so you can't actually include the endpoints. You don't really need to know. Well, you kind of need to know that, but it's not like it's a super important thing on this. What I usually think of in my head with mean value theorem is, for the ifs anyway, if it's continuous and differentiable. I don't even worry about so much about the endpoints because it's kind of just, I abstract that away. It does have to be true, but the main thing is the continuous and differentiable. So that means it has to be a smooth curve and no holes, jumps, or gaps. Okay, it cannot be this because that's not differentiable there. Okay, so in your head right now, I want you to think of a continuous and differentiable graph. So it's just a smooth curve. It could be a straight line if you want to. It's just there's no sharp turns on it. Okay, but think about that. No sharp turns, no holes, jumps, or gaps. So if you don't understand what continuous and differentiable mean, I would write that down. No holes, jumps, or gaps, and no sharp turns. That's what this is essentially saying. No holes, jumps, or gaps, no sharp turns. If that is true, then there is going to be a point that exists between A and B. So there exists a point C between A and B, such that the derivative at that point, this is the derivative at that point, is equal to this mess right here. And that basically is just the definition of slope. Okay? So if it's continuous and differentiable on an interval, there's some point C between A and B such that at that point, the derivative is equal to the slope of the endpoints. Now I'm going to draw this out so it makes more sense because this is still very, very confusing. It's very crazy. When we do an example, hopefully that makes more sense as well. So let me draw this out. And I'm going to say it's on the interval from A to B. Those are just any number. You could think of it as like -1 and 3 if you want to think about it less abstractly. I'm going to draw some function. Let's do it in red here. I'm going to go from here to here. Doesn't matter. And I'm going to kind of make it a little curvy here so you get something like that. Okay. First thing that I want to go on in your mind with mean value theorem is think, is it continuous? Is it differentiable? Okay, are there any holes, jumps, or gaps? No. Are there any sharp turns? No. So this is continuous and differentiable, which means mean value theorem applies. Okay, mean value theorem applies. Okay, now that means there is at least one point C. There could be multiple points. See, like already exists a point C. It should say point or points. It could be multiple. It doesn't have to be just one. In this case, there's multiple. Okay, where the slope of the endpoints, I'm going to actually draw out this line of the endpoints. The slope of this line right here, okay, it says that there's at least one point that has the same slope as the endpoint. Okay, so let me draw that out here. So here is the slope of the endpoint, and you can kind of imagine right here, drawing tangent line right there, where it's parallel with the slope of the line of the endpoints there. Okay, there's also another one here. You can kind of imagine grazing this point right here, pretty much the same slope, and then another point right here. Okay, you technically can have infinitely many of these, right? But not for this example. Mean value theorem applies, and so these would all be points C that I was talking about before. So I'm going to do like C sub 1, this would be like C sub 2, and this would be like C sub 3. All of these are points that have the same slope as the slope of the endpoints. Now you really need to have a deep understanding of this because you're going to have to apply this to certain contexts. Sometimes you'll be given a problem and you'll go, wait a minute, I don't know how to solve this problem, but really it's a mean value theorem problem in disguise. That's what I like to call it. It looks like it's not mean value theorem, but it actually is. It doesn't say it outright, you know, this is a mean value theorem problem, but it actually is a mean value theorem problem based on what the theorem states. Okay, I am going to try to make this definition a little bit better. Okay, there exists, instead of a point, at least a point, at least one point. So I'm going to put that over here. At least a point, at least one point C, such that this is true. Okay, there could be multiple. And C has to be between A and B. Okay, it cannot be equal to A or B. Okay, the reason why C cannot be equal to A or B, because if it was, like, say C was right here, you can't take the derivative at that because the derivative doesn't exist on both sides. Okay, it only exists on one side. Same with over here, it can't be over here because it doesn't exist on the left side. All right, let's get after it then. It says right here, find the value of C. Find the value of C guaranteed by mean value theorem. I'm going to write MVT from now on, so if you ever see that, that just means mean value theorem. Okay. So first thing you need to do, mean value theorem. If it's continuous and differentiable, is f of x in this case, for this example, is it continuous and differentiable on the interval from 0 to 2? It's quadratic, so that means it's smooth. It's also quadratic, which means it's continuous, right? And then smooth meaning there's no sharp turns. So because of that, it absolutely is. Mean value theorem does apply for this. If mean value theorem did not apply for a certain problem, you would just say mean value theorem does not apply. There are certain problems where you have to write that, okay, if there was a sharp turn. So this means that if we do the derivative of this at C, you're gonna end up with 2C for it. So that I did the derivative, which is 2x, plugged in C, you get 2C. This should be equal to, if I find the slope of the endpoints. So change in y over change in x. Okay, and you could solve for C then. Okay. Now f of 2, well, here's our f of x equation. So you plug 2 into that, you get 5. Minus f of 0 is 1 over 2 is equal to 2c. 4 equals 2, c is equal to 1. Then you have to check, is c between a and b? Yeah, 1 is between 0 and 2, so it's awesome. We're good to go. Okay. Now, just to cement this in a little bit more for you, I'm going to actually show you what this looks like graphically because I think it's just good to see a visual. Okay, I'm actually going to draw this one out. All right, here we go. Check this out. F of x, f of x equals x squared plus 1. Okay, but we're only going to be on the interval from 0 to 2. Okay, so it only looks like that. Let's blow this up here. Okay. Now, the slope of the endpoints, it said that it was, we got, what did we get from it? 2? So if you look right here, I graphed out 2x. Now, if you notice that 2x is parallel with the slope of the endpoints here. I'm just off a little bit because of, I'm off a little bit because of the y-intercept. So if I change that to a 1, it matches up with it exactly. Okay. Now, we want to figure out the derivative, the derivative at, what do we get, 1. It's equal to 2, which is what the slope of that is right there. So it works out. So I program this to, I want that. Okay. I program this to whatever function you put in here. If you change the endpoints, so say I change the endpoints here, oops, that's not fun. I'll just change it to this one right here. The endpoints here, let me get rid of, no, that's the endpoint. It'll actually find, right here, the slope of the endpoints, it actually finds the other point where that matches that slope. Okay, and you can put in whatever function you want in this. Let me do this. X squared plus 1, okay? And we're going from 0 to 2, Okay, I'm gonna stretch this out so you can actually see it. And you can see the slope, the line on the endpoints, and then the line at 2, or at 1, x equals 1. Okay. Okay. Now, it's easy to kind of, I mean, not easy, but like I can change this around where, you know, I had something like this from -4 to 2, and you'll notice the endpoints have a negative slope, and then it finds that other negative slope, and you can see that it's parallel. So now I'm going to show you something where it does not apply, just so you kind of get the idea. Okay, so this is kind of just a breakdown of the theorem itself. Okay, so we have this example right here that shows where it applies. I'm going to draw another graph here. There we go. Okay, so now what I'm going to do is I'm going to break the rules. It says it has to be continuous and differentiable. Okay, I'm going to use a pretty easy example on this, I think. So say I did something like this, a sharp turn. So I did a sharp turn here. Okay. Now, if you draw out the line from the endpoints, okay, you'll notice there is no point here that has the same slope on the graph. Okay, there's no point that has the slope, which means the derivative. Now you might go, well, and this is supposed to be a sharp turn. It kind of looks rounded off, but like you might be thinking, oh, can't you just do that? The problem with a sharp turn is you don't know where, here, let me zoom in here. You don't actually know where it's not meeting at one particular spot. So can I do a tangent here? Could I do a tangent here? Could I do a tangent here? There's infinitely many tangents. So because of that, it's not differentiable. There should just be one to be differentiable. So at sharp turns, you can graze it at infinitely many spots. Okay, so let me draw a sharper turn. So here's pretty sharp turn here. Okay, and then I'm gonna use purple here. So again, you get like I'm grazing here, I'm grazing here, I'm grazing here, I'm grazing here. You can just graze infinitely many. You don't have to go infinitely thin on this, but there's infinitely many lines you can make on that. Now compare this to if I rounded it off. Oops. I rounded it off. Okay. Let's do purple. Okay. You can only make one, right? You can only make one here where it grazes it once. Because if you do any of the other times, it's not really grazing it once, it's grazing something else. So you can't actually do it that way. I also kind of showed this before with the local linearization. If you zoom in, this would flatline. It's not going to work on this so much. It kind of looks flat. But a sharp turn is always going to be a sharp turn. That's why it will not work. There's no point that has the same slope as the slope of the endpoints here.